So once in a while, it's really important that we review some wisdom from experts long time ago and see are we on the right track? Are we doing the right thing? And today we are going to talk about two papers that we assigned. I don't know how many of you have read these two papers before, but in fact, in terms of system design, computer system design, they are the two most important papers that I would say that guides the computer system design for a long time. And these two papers, they are end-to-end arguments and hints in computer system designs. And in fact, I think no matter if it's within this class or other classes, if you have never read these two papers before, you really should go and look into this two paper deeply, because in the future, when you go on the job market, when you go on the interview, everyone is going to talk about this two paper. So, but before we talk about these two papers, let's remind ourselves what we have learned throughout this quarter. So in the very beginning, we talk about the roofline model. So in the past, when we talk about a memory-bounded application or compute-bounded applications, people typically just go with their intuition, saying that, oh, this is a compute-bound application. This is a memory-bound application. In fact, how do we know this? There is a very strict model that will help us understanding that. That is the roofline model. So, and if it's memory-bounded or if it's compute-bound, it's depending on which hardware you are running this application. So this is the figure that we use the roofline model to draw the roofline of running of different computer systems, different configurations. So you can see the first column is for each of the line, there is a dash before and after. So before the dash, that's the compute unit, and after the dash, that's the memory element. So so if you are talking about like an LSTM, for example, or say like a convolutional neural network, for example, if you talk to people about convolutional neural network is compute bounded. That's only true if you are using CPUs or using GPUs. However, if you are using TPUs, where your roof line is defined by the solid line with the square as the dots, you will figure out that if it's convolutional network, it's not compute bound anymore. Instead, it's going to be memory bounded. So again, as a scientist, as an engineer, nowadays, when you talk about something, you really need to back up by numbers, back up by facts, back up by truths. And the numbers, what really help us to identify if an application is memory bounded or compute bounded, you have to use the roofline model. So that's why we put this in the very beginning. And once you identify its compute bound or memory bound, you will have different solutions. So for example, if it's compute bound, then we have various solutions, for example, like AI ML accelerators to improve the compute efficiency of the core linear algebra operations. And for the GPU, it's general purpose vector processor. So for if your operation is mainly based on vector operations, then GPU is probably the best friend of you. However, if you have some algorithms that cannot easily be using matrix operations, matrix vector operations, or vector operations, some people suggest you can go with FPGA or build an ASICs to improve the compute efficiency. However, we also, but the thing, remember, hardware accelerator is going to improve the efficiency of computation. If you have an application that's memory bounded after applying it or before applying this hardware accelerator, then you have to be really creative about how can you tackle the issue of limited memory bandwidth. And turns out the solution that we came up with is either in-memory processing or in-storage processing. And sometimes the reason why we have the memory bounded problem is just because you didn't store the data right. So the last lecture we talked about how can we make the data storage in the right format. So before we start the lecture today, I think you guys read this paper. If you haven't read, it's really important right now. Look up that PDF and go into this paper and find out, discuss with your friends what's the end-to-end argument.
Basically, sometimes you want to, in a system design standpoint, you want to provide computation at a lower sort of node, I suppose. So think of it, I think, as like the computation at like an SSD, right? So I sort of understood it. Sometimes it's not worth it to put it there if
discuss.
Okay. So So for the SSD example, if you put computation in the SSD, is it worth putting it there? Yeah, a big part of it is basically talking about how the networking aspect, right? Where it's like, if we place it there, at this lower level, at this level interpreted standpoint or from hardware standpoint, is it worth it to have to move data? This communication and also like, is it worth it to even put it there? Why don't we just put it up here? Is it a Yeah, so a couple examples they had was error recovery, limited error. So if you see the security. You want to transfer from one node to top node. You need to add some sort of like encryption, some sort of what do you call it? Like RSA stuff like that. Duplicate memory.
All right, what's the end-to-end argument? As I mentioned, this is one of the most important paper in system design. And like whenever people ask you about system design question, it's hard to not referring to this paper, right? So what's the end-to-end argument? How many of you have ever read this paper from other classes? No? Never seen this before? Okay, I'm surprised. This should be a paper in operating system class. What's the end-to-end argument? This is very important. And in fact, this is probably like the holy grail in system design. Like every system design, you have to go through the argument, this argument before you decide.
I understood it as sort of the SSD computation example, where if you put computation in SSD, is it worth the overhead of moving stuff around with encryption and stuff like that?
Okay.
But I think it's more for like a distributed system rather than a hardware system.
Right. So where can you find in a paper? What's the end-to-end argument in the paper? What's the end-to-end argument?
The principle called the end-to-end argument suggests that functions placed at low levels of the system may be redundant or of little value when compared with the cost of providing them.
Okay, so there is one paragraph. The end-to-end argument, right? What's the argument itself in a paper? Okay, now I'm 100% for sure you guys didn't read the paper before coming to the class. What's the end-to-end argument? Okay, read it out loud.
The function in question can completely and correctly be implemented only with the knowledge and help of the application standing at the endpoint of the communication. Therefore, providing a question function as a feature of the communication system itself is not possible. Sometimes an incomplete version of the function provided by the communication system may be useful as performance enhancement.
Okay, this is the end-to-end argument. So when somebody asks you about what's the end-to-end argument, I don't want to hear other things. So again, this is like Bible. You cannot alter any word here. That's the end-to-end argument. When somebody asks you about, hey, have you heard about end-to-end argument? This is the standard answer and the only answer. You should memorize it. I'm serious. This is the end-to-end argument. The function in question can completely and correctly be implemented only with the knowledge and help of application standing at the endpoints of the communication system. Therefore, providing that question function as a feature of the communication system itself is not possible. That's the end-to-end argument. So this paper itself, if I remember correctly, they provide 3 examples, right? And one of the example is file transfer, right? And as you can see, there are 5 layers of networking, right? And the end-to-end argument suggests the only way we can know if the file content is corrupted or not is at the application. So it doesn't make sense to implement redundant features as the network infrastructure feature. That's the end-to-end argument, right? And so the thing is like, okay, so some of the reasons that you might suffer from the corruption of file content is probably like your either host A and B crashes, or there is a hardware failure at the end in some of the component, or you lost the network connectivity, so your packet never gets sent out, right? So those are the potential reasons you get you won't be able to get correct file on the other end, right? But the thing is, the real implementation nowadays, like if you know the internet well, right? We do error checking at the transportation layer. We do error like checksum in the link layer, right? And we would request the resending of packet at a transportation layer if you use TCP, right? And also at the link layer, depending on which MAC protocol you are using, right? Typically, you would also ask the packet to resend if you didn't receive the data frame, right? So the thing is that we have implemented a lot of retry timeout redundancy function. And the end-to-end argument suggests, right? If you just implement stuff on the application layers, it doesn't hurt those functionality. And potentially, you can make your lower layer more efficient. That's the end-to-end argument, right? So the thing is that the key idea in end-to-end argument is that sometimes in system design, we think we should provide some of the features at the low level. And we want to make those features very reliable, very perfect. However, is that necessary, right? So that's the implication of end-to-end argument. So that's why I'm saying the end-to-end argument is by far the most important paper that guides all the system designs nowadays, because every time when you design a system, when you have a layered system, you have to go through this end-to-end argument to convince yourself it really works to pay the overhead of redundant functions instead of purely implement everything at the application level, right? So as a summary of the end-to-end argument, the reason why we don't want to provide features at the lower level, instead of only providing features at the application layer, because without the right knowledge, first of all, you're not going to implement that feature correctly, right? So for example, without the knowledge of, right now we are running machine learning applications, we might not know at what precision we really want for matrix operations. So if you offer matrix operations at a very low level, you may end up overly accurate in computation, which is unnecessary, right? So that's what the end-to-end argument would lead to, right? And so there's always a trade-off between performance and cost. And here's the reason why. We implemented stuff like AI accelerator because the performance gain is really large, right? So that's why we end up want to pay that overhead of implementing that at the low level, right? And so this is an important thing, right? So now we have remind ourselves what is the end-to-end argument. Go through all the ideas that we talk about in this quarter. What ideas follows the concept of the end-to-end argument, and what ideas is against the idea of end-to-end argument?
specific lower layer hardware change, you're making something that doesn't apply application level. Yeah, so that would be an example that doesn't work for end to end, right? Because you're making a hardware change that doesn't apply to the application, and you're adding features that you might not need. So it doesn't work for end to end. I think that means in general. Because you're making a very specific hardware change that doesn't work at application. Maybe? Am I just making all arguments like this?
I wouldn't say it's like a specific to that, but it's kind of just been a theme, which is that you have to look and like kind of look at your whole system before like the operation of one component in isolation is not enough. So you have to look at your whole system and how things are affected. So I feel like that kind of both goes in support and also like in certain ways. Like the
Basically, like,
oh,
okay,
like
for
specifically
example,
like the topics.
like for there had to be what else we got.
Yeah.
GPU Direct doesn't follow this, right? Because you have GPU. I mean, it's like a well, yeah. No, GPU Direct was like well, the thing is like you're implementing this, right?
Yeah.
Yeah. But you need to kind of like know, right? Right. What was asking is if like the default was using.
Yeah.
No, it's not right. It was an application level specific thing that you use GPU Direct.
Okay, what ideas you have learned against the end-to-end argument?
Most sort of hardware, like an ASIC, is kind of against it because.
Okay, ASIC is against it.
Sort of, unless I'm misunderstanding. The way I see it is, if you're making an ASIC, right? It's a specific device that does one specific thing, and if the application doesn't use it at all, then it's useless, right?
Okay, so ASIC is one of the example. You guys think it against the end-to-end argument?
Well,
What else? Near data processing. In what way?
Kind of like adding more layer to have a computation of that processing, and you may not need that necessarily. So you can do the like data processing on CPU instead of need that actually computation.
Oh, okay. So let's review again. What's the end-to-end argument? Providing the question function as a feature in a of the communication system itself is not possible, right? So what does that mean is that is talking about if we add function, add a communication system, like the networking example, right? It's below the application layer. And it's something that every application has to suffer, have to go through, right? So on the other hand, another like more verbal way or generalized way of talking about end-to-end argument is that we should always thinking about if we should place a function in question as a feature at the infrastructure. And the infrastructure in a host computer system is pretty much like the memory hierarchy, right? So what does that mean is like, or the networking or the I/O subsystem, because that's something like every application will use, right? So to that perspective, I would say in storage processing, in memory processing, they are really against the idea of the end-to-end argument. And in fact, from what we have learned, right? Do you remember that I was talking about in-memory processing and I say, well, this idea at the end, it failed, right? Why? Right? When I talk about in-storage processing, at the end, this idea failed. Why? Because without the knowledge about what's the application we are running, these features, they are useless. So it turns out we have to modify the application, right? So that's not, so, and those leads to the failure of those ideas, right? So that's why I'm saying end-to-end argument matters. If we could have thinking about end-to-end argument. So first of all, I want to say that's there is a very interesting like there is a very interesting like gap between academic research and commercialized product or a successful commercialized product or successful idea. In storage processing, in memory processing, we publish a lot of papers out of it. So academic-wise, that's a big success because it helps a lot of people getting PhD, helping a lot of people getting like awards, helping a lot of people getting tenured. However, commercially or to the real world, if you cannot pass the end-to-end argument, these ideas, any ideas that cannot pass the end-to-end argument, it's not going to success. Remember this. Any system design ideas, if you cannot convince yourself, it pass the bar of the end-to-end argument, it's not going to be successful, right? So how about TPU or GPU, right? Like you guys saying that in the very beginning, I know, Aaron, you immediately thought about ASICs, right? This sounds like an idea that's against the end-to-end argument. However, why this idea seems to be against the end-to-end argument, but it becomes successful?
I think it, while like from the general perspective of like considering the application that's using it, it's very specific to a particular application. That application is so critical and important that you can afford to not consider the other things that won't utilize it.
Okay, so that's a good point, but I would say let's go back and read this end-to-end argument again. I feel like today I'm teaching preaching a sermon or something, right? Let's go back and read this end-to-end argument again, right? It's pretty much like on Sundays when you go to a church, right? Like the pastor saying that, let's read this verse again.
So maybe the reason why GPU are kind of successful is because unlike a communication system, not all applications have to go through it. You send the application to them, and so you only use those when you need it.
Okay, so here's the thing, right? Why am I referring to this? Right. The answer is actually in this argument itself. Right? Okay, so here's the thing. There are several ways we can interpret why GPTPU or say like GPU, they become successful, right? Why those we have a lot of hardware accelerators, right? But in fact, GPU becomes successful. Later on, ray tracing accelerators become successful. And later on, AI ML accelerators become successful, right? But other accelerators that you have, digital signal processor, DSP becomes successful, right? So there are indeed some additional spatialized hardware becomes successful. But why? Right? So the answer is very interesting. First of all, hardware accelerators or application-specific accelerator, right? They call it application-specific because when we design this hardware, it's tightly coupled with the application themselves. So when you design this hardware, you do have the knowledge and help of the application standing at the endpoint of the computer system. So that's why I'm saying the answer is actually in this argument itself. This function in question can completely and correctly be implemented only with the knowledge and the help of the application standing at the endpoints of the communication system. And for those application-specific ICs or the GPU or DSP or ray tracing accelerator, they already know the narrow set of target applications. Question?
If we go back to the near data processing example, so if we now have a new application that's important enough, and we only use this, for example, Smart SSD, to store that application's data, would that be in support of the argument?
It will support the first part of argument, right? So that's why in the very beginning, the Smart SSD paper comes with the SQL database query, right? But then, what's after? Sometimes an incomplete version of a function provided to the computer system may be useful as a performance enhancement, right? Because you are not able to run the whole application simply on that accelerated hardware. So it must satisfy the last part of this argument. It must be a performance enhancement, right? So let's go back to the question of Smart SSD, right? Do we see surprisingly good performance in general? Sometimes yes, right? If your selectivity is low, if your number of columns is low, is high, right? However, that's based on the criteria, right? And even with that, your performance enhancement is limited because the processor that you can put in Smart SSD is really limited, right? But that's not the case for GPU, TPU, or ray tracing accelerator or DSP, right? So if you really want to have something application specific, if you really want to add something to the infrastructure, that has to have like maybe 2 figures of speed up instead of like just 30%, 40%. Again, 30%, 40%, that's good enough for a paper. But in reality, no one is going to pay that overhead unless we get 2 figures of speed up, right? So, and also, how can you make this function generally useful? You need the knowledge of application. So that's why when you guys have the project meeting with me, I keep asking, what's the application? What's the application? And in fact, you should remember, when you start up a project, that's why in the very beginning, right, sometimes you feel like, okay, the startup company boss, he is not doing anything, or she is not doing anything. She is like consistently visiting customers. She is consistently giving talks, like TED Talks, instead of doing some useful things. Why is that? Because we want to hear what the general audience really wants. So that's why reaching out is very important. And also, like commercially, you want to know what the customer want instead of like just rolling out new features and ask customers to use it, right? Because I oftentimes work for some companies. I don't want to say which company is that, but you can easily find from my resume. But the thing is that we always starting from the perspective that, okay, somebody told me that we have this thing. Can you help us finding the use case of it? But thinking about this is wrong in the very beginning. You should think about what's the use case before you go and do it. And when you go and do it, you have to pass through this end-to-end argument. Can we implement this function as useful as we want? Can we implement this function as performing as we want? Right. So that's actually the 2 most important implications from the end-to-end argument. If you really want, it doesn't say that you should not add a function in the infrastructure. It means that if you really want to do this, think about these 2 questions. Can this function be useful? And also, not just useful, but also performing, right? So what does that mean is that in-story processing, in-memory processing, because we have insufficient amount of the application inputs. So we have no way to know at what degree we want this function to be. We have no idea about what the application really wants, right? Okay, but the same thing doesn't apply to GPU and TPU, because the speed up we see for gaming, it's hard to imagine right now you play like a 3D game without having a GPU, right? It's hard to imagine you want to do some reality workload without a ray tracing accelerator. It's hard to imagine that you want to do inferencing without a GPU or an AI accelerator, because the speed up is too significant. And the benefit worth us to pay that cost, right? So that's the thing about end-to-end argument. Okay, another paper is the hints for computer system design, right? So I know you probably didn't read this paper, right? But here's the thing. The hint for computer system design, it actually lay out a set of rules, right? So you can think about like, okay, the end-to-end argument is pretty much like a Bible verse, right? And this is like the 10 commandments in the Bible that tell people don't do this, don't do evil, don't do something, right? So this is probably, so a lot of people would compare this paper with the end-to-end argument. They think that's one against another. The answer is no. This is actually a concrete. So if you are too lazy about understand the real insights from that simple verse of the end-to-end argument, these are the guidelines you should go through before the system design. For example, separate normal and worst case, right? So in what we have learned, Amdahl's law is something that can help us to separate the normal and worst case, right? So we should figure out what's the normal and the worst case. So the guideline here is that for the normal case, we want to make it fast. For the worst case, we want to make it right at least, right? And shared load end-to-end, but safety first. The safety here does not mean security, but means correct, right? So no matter what you want to do, it has to be correct, right? So that's the guideline, right? And it mentioned end-to-end several times, like for the speed, right? So the thing is that, okay, so the thing it mentions here, right? Speed, is it fast enough, right? You can definitely shed load, you can definitely do end-to-end. However, no matter what you do, it has to be safe enough. Means that you should not hurt the correctness, right? And also, fault tolerance. What if something happened, right? Again, you should do it end-to-end. You should have an end-to-end guarantee, check if something is working or not, right? Interface-wise, do one thing well at a time, right? So don't generalize it, get it right. That's why we have the application-specific IC, right? Or hardware accelerator. We try to do one thing right at a time instead of doing a lot of things, right? And fault tolerance log updates is a good idea. So, you know, like we have log file system everywhere, right? And we do log everywhere. And like FTL, that's an idea that we learned about log updates. And implementation, so there are other things that you should also thinking about. Don't hide power. So if you have an underlying feature, you should expose it to the upper layer so everybody can use it. And if you could have used, if you can provide more arguments, that's more welcoming, right? And leave it to the client. So again, because the application is the only one who has the right knowledge of implementing some function correctly. If you don't know what decision to make, don't make it at your module. Instead, just leave it to the client, for example, the application. And keep the basic interface stable. This is something that NVIDIA does very terrible, right? But it's not a very good example, but the thing is that because they are in monopoly, so they made it happen. But I want to say the failure story of TensorFlow, right? TensorFlow used to be the most popular machine learning framework. However, after migrate to TensorFlow 2, it becomes completely failure and PyTorch catches up. Because at that time, TensorFlow 2 interface is incompatible with TensorFlow 1 in many perspectives. And since we have to modify the software, why don't we just use PyTorch, right? So if your interface change is significant enough, then you must evaluate what's the risk of losing your customers, right? And other things, like if you can, again, the interface should be fast, be efficient, right? No one wants to have a user interface that loads forever, right? And also, if you could do static analysis, you should do static analysis first, but should provide the flexibility through dynamic translation. And also the implementation part, plan to throw one away. So this is very important, right? So a lot of cases, we want this, we want this, we want everything. right? And also, in many companies, they also like to see if there are competing ideas from one group to another. Why? Because they follow these rules of plan to throw one away. They always plan not implementing everything. Instead, they just leave the most valuable stuff to implement instead of putting everything all together, right? So keep secrets. The keep secrets, it doesn't mean that you should not open source. It just means that you should not reveal the implementation details too much to your user. What does that mean is that if go back and read to the interface, if your interface is simple enough, if you provide a sufficient argument, you don't need to let the user know what exactly your module is doing to make it efficient. That's the implication of it. And use a good idea again, right? So if this is a good idea, you should think about reuse it, right? So one of the things that you have been seeing everywhere in the system design is caching, right? You have buffers everywhere because it's a good idea, right? And divide and conquer means that if it's a big problem, you should try to divide it into small problems and solve it gradually, right? And speed-wise, you can use caching, you can use hints, and use brute force, right? So a lot of people with so that's why if you go to like a gaming company, because gaming is actually one of the area that really needs speed, you will figure out these are the people who doesn't like those like pointer-based data structure at all, right? Everything is in array, right? So that's why a lot of cases when you play the game, it crashes because of the memory violation. Why? Because brute force, right? And computing background, we have seen that, right? Batch processing, this is especially true, right? So you can see like how these two papers affects our system design. So it's always important that you should remind yourself regarding these two papers when you decide to apply any features that you have in mind for the data-centric computing. So this is actually my conclusion for this class. And right now, it's about the time for the project presentation. So who is